All right, let's dive right into this explainer. Today, we're unpacking a profoundly rigorous, deliberately anti-hype framework known as distinction theory. We're going to look at a deeply foundational question here. Not just how the universe behaves, but what must logically happen the precise moment a finite system separates itself from the rest of the universe. This isn't about magical thinking, It's about inescapable mathematical constraints.
Think about this mind-bending, yet honestly kind of intuitive premise. Existence isn't free. Finite systems actually pay to maintain their boundaries. The simple initial act of separating self from not self is the ultimate origin of all systemic costs. The moment you draw a boundary to define an identity, you're suddenly a finite entity existing in an incredibly vast environment. And that structural reality, it sets off an absolute, inescapable chain reaction. To keep everything structured and totally auditable, we'll follow this precise agenda. We're going to hit the logical cost of existence, the deficit dissipation spiral, the theory's tiered guardrails, some domain applications, its strict failure conditions, and finally, the ultimate fate of systems. Okay, Section 1, the cost of existence. Let's see exactly how this entire framework builds from a single, undeniable, logical primitive. Before we even touch physics or thermodynamics, there is the fundamental logical act of distinction. To be something is to be distinguishable from what it is not. Any attempt to coherently deny this principle actually performs it. Think about it for a second. By trying to separate your denial from the thing you're denying, you're drawing a boundary between your statement and the concept itself. You're making a distinction. It's a completely self-verifying mathematical primitive. Now, notice the strict separation here between the overarching framework and its mathematical engine. Distinction theory is the broad research program, but its beating heart? That's Active Finite Distinction Systems, or FDS. This is the formal mathematically restrictive core. We aren't dealing with vague philosophy here. We're dealing with systems that actively maintain a boundary through state-dependent updates under finite representational capacity. Which brings us to Section 2, the deficit dissipation spiral. This is the relentless logical engine that drives all finite systems, the core causal chain. So here is the crucial point, this unbreakable chain. Once you have a boundary, you have a finite capacity. Because you're finite, you face a capacity deficit. That deficit forces you to use lossy approximations of the world. Those approximations inevitably lead to errors, which require irreversible corrective updates, which then culminate in a thermodynamic cost as heat. And when that cost piles up, you face a severe choice. Let's unpack that first big step, the capacity deficit. Because a system is finite, it literally cannot perfectly model an environment that's strictly larger than itself. It's mathematically born with a capacity deficit. Imagine a tiny hard drive trying to download the entire internet. It structurally cannot hold the complexity. This isn't just a practical engineering limitation or bad design, it's an algebraic necessity. The universe is always going to throw more at you than your internal budget can track. And this perfectly captures the physical tax the universe charges for that deficit. Because your models are imperfect, you've got to constantly update them just to survive. Under the Landauer principle from physics, every single time a system irreversibly updates a model, erasing old data to write new data, it dissipates at minimum kBT ln2 of energy as heat. Every distinction operation has a physical thermal footprint. You're literally burning free energy to process the difference between your model and reality. Eventually, the maintenance cost of these models is going to blow past your available energy budget. When you hit that ceiling, the system faces exactly 3 mathematically permissible fates. You can prune, meaning you actively burn energy to erase inert complexity. You can externalize, shifting that maintenance burden onto your environment or tools. Or you experience a saddle node bifurcation. That's a sudden, catastrophic phase collapse, where you completely lose boundary maintenance. Moving right along to Section 3, a tiered research program. Let's establish the architectural guardrails of this theory because they are incredibly strict. It is absolutely vital to understand what this theory is not. This is a calm, rigorous framework of constraints. It is definitely not some megalomaniacal theory of everything. It doesn't claim quantum field theory or general relativity are wrong. It doesn't magically derive the speed of light from scratch. It doesn't solve consciousness just by casually asserting it. And it doesn't solve quantum measurement by assertion either. It strictly aims to explain why existing structures might be necessary under finite system constraints. To manage all these claims, the theory acts a lot like a software operating system with tiered dependencies. Layer 0 is the pure mathematical core containing the absolute minimum kernel. Layer 1 forms a physical bridge, like Landauer's principle, and Layer 2 contains speculative domain applications. This means if an outer application fails, say a specific hypothesis about biology is proven wrong, it doesn't arbitrarily destroy the core algebraic spine of the minimum kernel. The failure only propagates downstream. Let's hit Section 4, Applications Across Domains. We'll quickly survey how this deficit dissipation spiral maps onto complex domains, safely quarantined behind those physical bridge assumptions. What's truly amazing here is how the exact same thermodynamic math applies absolutely everywhere. In biology, life is defined as the emergence of the first active pruning operator, a chemical network actively burning energy to degrade its own waste. In AI, agents face rigid rate distortion limits when their causal capacity overflows. In civilizations, we see societal collapse when institutional residue, like outdated laws, outpaces a society's governance capacity to prune them. But it extends even further. It extends to physics, where time itself manifests through irreversible distinction updates. It touches on theories of the observer and consciousness, mapping the exact boundaries of where active distinction begins, and defines fundamental death as the cessation of that active boundary maintenance. The scale changes, sure, but the thermodynamics of the boundary remain identical. That takes us to Section 5, Falsifiability and Failure. This is honestly my favorite part, how the framework actively invites its own destruction. There's this quote from the archive that hits the nail on the head. A theory that cannot die, cannot touch truth. Distinction theory does not want to be protected by vague philosophy. It offers its own explicit, pre-specified death protocols, and flat out asks the scientific community to judge it by them. Look at how seamlessly a failed claim triggers a specific consequence here. A failed claim is never just reinterpreted so the theory can survive. If someone finds a valid mathematical counterexample to the minimum kernel, the entire theory dies immediately. If a physical system is proven to irreversibly erase data below the Landauer limit under specified thermal conditions, the physical bridge is instantly demoted. And for the biological bridge, well, if you can demonstrate a completely passive network capable of sustaining infinite complexity without any active pruning, that specific bridge fails. It is completely auditable from top to bottom. Finally, we arrive at Section 6, the last invariant. What happens to systems that can no longer pay that boundary tax?
The core dynamics reveal that systems naturally bounce between two distinct phases. Phase A is exploratory burning. This is when the system has excess free energy, generates incredibly complex models, and innovates rapidly while dissipating a massive amount of heat. But eventually, the budget runs out, triggering a severe collapse into Phase B, persistent residue. The collapse burns away absolutely everything that's too energetically expensive to maintain, leaving only a pruned, low-energy baseline. So what actually makes it through these brutal cycles of collapse? It's not always the strongest, the most complex, or the most temporarily adaptive structure. What persists is what no local noise can erase, an invariant. These are topological features, conserved quantities, or deep symmetries that are inherently cheap to maintain because they don't require constant, active memory updating. Think of a core mathematical truth or a fundamental particle's charge. These are things that require essentially zero active energy to remain structurally true.
Which brings us to the profound core of this entire explainer. Distinction theory studies the inescapable tax that all finite systems absolutely must pay simply to exist and actively maintain a boundary against the universe. It leaves us with a strictly auditable structural question to ponder. In a universe governed by the capacity deficit and the relentless thermodynamic cost of constantly updating our imperfect models, what truly remains of us, our AI or our civilizations, when the free energy finally runs out?